Well, hello there, and welcome to your first 3C lecture video. One of the coolest things that we're going to do this semester in 3C, or at least in my opinion, one of the coolest things, is learn how to measure the wavelength of light. That's an extraordinarily small quantity, which is why it's cool that we can do so. But in order to do that, we have to be very familiar with wave phenomena, the vocabulary of waves in physics, and in order to do that, it really helps to be familiar with what's called simple harmonic motion. And it's time to review simple harmonic motion. And I say review in air quotes because probably many of you have not yet learned this topic. That's true particularly if you took your mechanics class with me. So here's Chris Farley in his air quotes. Let's review simple harmonic motion, hence the SHM. Perhaps the most familiar example of simple harmonic motion is the mass attached to a Hooke's law spring. So an ideal Hooke's law spring is massless itself. M is the mass attached to the end of the spring, and if the mass were not attached, I always forget to grab my laser pointer here. If we were neither pulling nor pushing on this spring, it would have what's called an equilibrium length. And in the top picture here, this spring is at its equilibrium length. If you give the spring a pull to the right, you've now stretched the spring, and we know that means you've stored energy in the spring, and the spring's going to pull back on this mass, hence this little vector symbol F, indicating a force to the left. And we use the variable, or right now I'm going to use the variable x to denote the displacement of the end of the spring from its equilibrium position. So the end of the spring corresponds to the position of the mass. And right now, because the spring has been stretched, typically we consider that to be a positive displacement. So here x would be a positive quantity. In the bottom picture, we've compressed the spring, pardon me, and x now has a negative value. And of course, the spring is going to push back on the mass. That's why this force is directed to the right. Hooke's law is a very simple statement, and it was first, this is probably fairly obvious to a lot of people. This might be your first guess if you were trying to come up with a simple theory of the behavior of a spring. But perhaps the first person to write it down mathematically was this guy, Mr. Hooke, a contemporary of Newton's. And he made the simple observation that the strength with which the spring pushes back or pulls back on the mass is just proportional to the magnitude of the displacement. In other words, if you were to stretch the spring, if you were to stretch the spring twice as far, the spring would pull back twice as hard. If you stretch it 3 times as much, it would pull back with 3 times the force. Graphically, that means if you were to plot the force of the spring versus how far you had stretched it, the data points that you would get fall on a line. There's a linear relationship. Saying that 2 quantities are proportional is equivalent to saying that when you plot them against each other on a Cartesian graph, you get a straight line. Now, obviously, if you stretch this spring hard enough, like instead of 5 pounds or 10 pounds, what if you pull it with 1,000,000 pounds of force? It's going to break well before that. And before it breaks, it'll probably start to stretch and, metal fatigue and all that. So real springs only obey this relationship over a rather limited range of displacements. But the ideal Hooke's law spring would satisfy this relationship over any range of displacements. Now, if you want to write this down technically, you would have to, you could replace this proportionality symbol with an equal sign, and you put what's called a constant of proportionality out front. You stick a minus sign to reflect the fact that when the displacement is positive, the force from the spring is directed opposite to the left. So the spring force always has the opposite sign from the displacement. That's why we need the minus sign. And K, which is often called the spring constant. You could also think of it as the stiffness. That's exactly what it is. It's a measure of how stiff the spring is. And graphically, that would be seen as the slope of force versus displacement. So hopefully you've done a lab like this in your mechanics class. You took a spring and you hung several weights from the spring and you plotted the weights versus how much the spring stretched for the corresponding weights, and you took the slope to get the stiffness. And it's an important thing to note here that the spring provides what's called a restoring force. It tends to restore the mass to its equilibrium position. Later, when we talk about waves on strings, we will also be talking about a restoring force. Okay, so most likely none of that is new, but now it's time to look at the so-called differential equation that describes the motion of this mass on the end of the spring. So we've established this. Hopefully you've seen that experimentally. And you also are familiar with Newton's second law, that the net force on any mass is equal to the product of the mass and its acceleration. So right now I'm being careful to specify that I'm using Newton's second law along the x-axis in this picture. So I'm going to look at forces in this direction on the mass and equate that with the product of the mass and the acceleration. So since the only force, let me back up again, there's no mention here of friction horizontally or air drag. If the only force acting on this mass is the spring force, then we can take this spring force and plug it into the left side of Newton's equation, and we get this. So this really just says F, which is Hooke's law of force, equals ma. Well, what is acceleration? It's the time derivative, or the rate of change, of velocity, and velocity is the rate of change of position. So hopefully you remember from mechanics that acceleration is the second derivative of position with respect to time. And often in physics we like to use a more compact notation. Instead of dealing with the D's and the T's, I'm going to rewrite this in just a second here, but I've put a blue rectangle here just to emphasize this is an important equation. You're going to see an equation like this often. You'll see it again in this class and definitely in future classes. So here's the alternate notation I mentioned, and I think Newton maybe is the one who introduced this. Let's go with the double dots. Two dots above x indicate two derivatives with respect to time in particular. Time has a special status there. When you see dots, that means differentiation with respect to time. So it's a nice compact notation, and it has that extra meaning of being a derivative with respect to time. So let's make that replacement here and move a couple things around. Whoa, what's this? I'm reminding you here that the x-coordinate of the mass is a function of time. What we're really interested in here is how the position changes with respect to time. We would like to predict theoretically. Of course, we could just go into a lab, put a mass on a spring, and record it and describe it that way. But wouldn't it be cool if we could predict theoretically how it should behave ahead of time by bringing Newton's second law to bear on this very simple mechanical system? So never forget here that the x-coordinate depends on time. It's a function of time. Usually we just write x, but if this was a math class where we were overly pedantic and we liked, using more ink, as much ink as possible, we would always write x parentheses t. But in physics we're lazy by comparison, at least in that respect. Okay, so if I move the m over here and I just flip the two sides of the equation, here's a nicer way to write the basic dynamic equation that describes the behavior of this mass on the spring. Now, what does this equation say? Well, the second derivative of position is some negative number times the position. Now, how can we interpret second derivative graphically? You all remember that the first derivative of a function gives the slope of the tangent line to that function. And the second derivative is the rate of change of the slope, otherwise known as curvature. Remember that? Concavity, you've got concave up or concave down. So what this equation tells us is that for this mass moving around while it's attached to the end of the spring, at any time, at any point in time, and I really should have put the variable x up here, if you plot the position of the spring versus time, the curvature of that function always has the opposite sign from the value of the function itself. And maybe I should go back a couple slides. So we all know from experience what this mass is going to do. It's going to bounce back and forth. So the graph that you just saw, when the mass is to the right, that will be represented by x coordinates that are above the t-axis, and when the mass is over to the left of equilibrium, that will be represented by x coordinates that are below the t-axis. So back to this graph here. When the x coordinate is up here above the t-axis, that means the mass is off to the right, positive displacement. When the x coordinate is negative, we know that that represents negative displacements. Okay, so what do we observe about the curvature right here? This is concave down, right? The slope is decreasing. So here's where the second derivative would be negative, but the equation says that if the second derivative has a negative sign, the value of x itself would have to be positive, right? Minus a positive number would be a negative number. So does the x-coordinate have a positive number? Yes. Right here, the x-coordinate is positive. Remember, the vertical axis here represents the x-coordinate. It is positive, and the curvature is negative. Down here, the x-coordinate is negative. This is when the mass is off to the left of equilibrium, and the curvature is positive. And you can confirm that that's true everywhere on this graph. The curvature always has the opposite sign from the position of the mass on the end of the spring. And what does this motion represent? Well, just a little thought, I think, will show you that this means that the mass is oscillating. It's moving back and forth, to the right of equilibrium, to the left of equilibrium. Now, this picture happens to show what's called damped oscillation because what we call the amplitude is dying down in time. I really should have included a graphic here that shows what happens if the curvature always has the same sign as the coordinate. So you'll just have to use your imagination here. Right here, the x-coordinate is positive. What if the graph was also concave up? So not only was the x-coordinate positive, but its second derivative was also positive. Instead of scooping back down to the t-axis, it would be scooping up. And you might be able to see that that would mean the mass just continues to move away from equilibrium. Same thing down here. If the x-coordinate was negative at the same time that the curvature was negative, then instead of scooping back towards the t-axis, or I guess this is a little confusing because the t-axis is down here. Let's pretend this is the t-axis. Yeah, this is every point on this line has an x-coordinate of 0. If it scooped away so that the curvature had the same sign as the displacement, again, the mass would be moving away from equilibrium. And that is certainly not oscillation. That's not what you would expect if you had a restoring force. Remember, though, the basic characteristic of the motion is that it always moves back towards equilibrium. Okay? So, to summarize, when the second derivative is proportional to the displacement, but that constant of proportionality is negative, you know you're talking about a very simple mechanical system with a Hooke's law type restoring force, and you can expect that mass to oscillate about equilibrium. It will always be brought back towards equilibrium. Now here's an example of oscillation, and let's see if we can figure out why this is not physically realistic. So this does represent a mass which is moving away from equilibrium, passing back through. Here the mass will be moving off to the left, moving back towards equilibrium, continuing through equilibrium off to the right, etc. Is there anything unrealistic about this graph? Well, first of all, what's the curvature right here? What would be the second derivative? You see that the slope is constant. The slope is the first derivative. So if the first derivative is a constant, then the second derivative is 0, right? The rate of change of a constant is 0. And you can also just see that the graph has no curvature in this region. So on the left side of the equation here would be the number 0. Everywhere in here, the curvature would be 0, but on the right side, we would not have 0. For instance, in here, we've got some negative number for x. It's not 0, times k over m, still not 0. So the equation is not satisfied. So this is not a physically possible motion. That's assuming that Newton's second law is the correct description of the dynamics. This type of motion would not satisfy Newton's second law, and so we kind of have to rule that out. This is called a triangle wave, by the way. Bogus, no good. So I've got a little video, this is the best I could find, of a mass bouncing around on a spring, and watch it carefully to see if you can observe why the motion doesn't really match this picture. Where's the play button? Whoa, I don't know what's happening here. There should be a play button. Okay. Can you see it? It's a little fast. Here, let's tilt it on its side. Maybe that makes it a little easier. Any better? So the x-axis is moving horizontally, or points horizontally like this. I think we need a slower video. This ought to work. I took this off of Wikipedia. So look at the position of this mass in time. And again, you have to do that mental maneuver in your head where you convert left-right displacements into up and down displacements on the graph, because it's customary to use the horizontal axis for time. So motion to the right corresponds to movement upward on this graph. Do you see how the speed is changing? The mass moves quickest in the middle of its motion, and then towards the end it has to slow down in order to stop and turn around, right? In order to turn around, you must first slow down and stop just for a moment. And if you look at this unrealistic graph, remember the slope of position versus time gives us velocity, the absolute value of velocity is speed. You can see that the speed is constant in between the turning points here. That's why this motion's not physically realistic. So we can just use our common sense to see that, and we can also use the argument about the curvature. So what might correct the motion would be to round off the corners of that triangle wave, because then you can see that the slope does gradually decrease to 0. Then it picks up speed again. The slope has to decrease to 0, indicating that the mass slows down and stops before it turns around. That would be much more realistic. And obviously, that's a shape that you're going to recognize, right? The red curve here is what we call sinusoidal. So let's see now if we can prove, perhaps, or show mathematically that sinusoidal motion is the actual motion using this differential equation. Now, why is it called the differential equation? Because not only do we have some unknown quantity x, which depends on time. Time is the independent variable. We also have a derivative, in this case a second derivative of that function. So this is an equation that relates this quantity x to its variable t and the derivative, or a derivative of x. So a differential equation is an equation relating functions and their derivatives, I suppose you could say. Okay, so for convenience, let's introduce a new quantity. This is a constant, and we'll call it omega squared. And this is almost universal notation. You'll find it in your book and practically every other book. This quantity k over m, let's just call that omega squared, which of course is the same as saying that omega is the square root of k over m. So take the stiffness of the spring, divide it by the mass, take the square root. That is this quantity called omega. It looks like a W. It's not a W. It's the Greek letter omega. Well, that means we can rewrite this equation as such. And now it really looks kind of simple, right? The second derivative is proportional to the function, and that constant of proportionality has a negative sign. So if you've never encountered this problem before, see if you can figure out right now if you're familiar with any function or functions for which the second derivative is proportional to the original function with a minus sign. Think about all the simple functions you dealt with in first semester calculus. Which ones kind of recreate themselves when you take the derivative twice, but with a minus sign? You know, like, is it x squared, x cubed, e to the x? I'm kind of leading the answer here, but let's try this solution, or let's show that this is one of the obvious solutions to this differential equation. So this may be one of the two simplest differential equations you can imagine, and if you take that class, you'll probably encounter it on the first day. So let's try the solution x equals cosine of omega t, because we already have a hunch that the motion is sinusoidal. We know it's oscillatory, and we've already established that that sinusoid makes more sense than the triangle wave. In order to check whether this function is a solution of the differential equation, we need to know what its second derivative is. So let's first take the first derivative. we know that the cosine turns into a negative sign, but don't forget the chain rule. We also have to differentiate the inside with respect to t, and that pulls out a factor of omega. And this is the velocity, right? X dot means d dt of x. It's the first time derivative of position. Let's take the derivative once more to get the acceleration. Now the sine turns back into a cosine, and the chain rule brings another factor of omega out front. So the second derivative of x, if this is x, so assuming that this is x, the second derivative of x would be negative omega squared times cosine of omega t. But check it out. Cosine of omega t, by assumption, is x, right? So we can just replace this with the quantity x. That's the position as a function of time. There it is. So what we've just shown is that if the position is given as a function of time by the cosine of omega t, then the second derivative of that position is indeed negative omega squared times x. We've shown that this function is a solution of this differential equation. Again, it's a very simple differential equation. It wasn't challenging to find a solution. If you tried some other function like e to the t, and maybe you could do this on your own paper, you'll find that the second derivative of e to the t is not, in fact, equal to negative omega squared times e to the t. You know, you could try e to the omega t or t squared. Try any number of goofy solutions you can think of, and I think you'll find that this is really the only one that works, or sine of omega t. Either one would work. I chose cosine because that's kind of customary. Okay. So I will remind you that this quantity omega, you calculate it from the square root of k over m. And if we go back to the function here, cosine of omega t, hopefully you're familiar with, well, of course you're familiar with trig functions. You're taking 3C now. But this quantity is proportional to the square root of the stiffness. So since that's in the numerator, that suggests that a stiffer spring with a greater value of k would perhaps oscillate more quickly. And I'll convince you of that with a graphing calculator. But the frequency, we call this the frequency, at which this thing bounces back and forth is determined by the stiffness of the spring, and also, of course, by the weight attached to the spring. It's fairly intuitive that the more massive the weight is, the harder it is to accelerate it, in other words, to shake it back and forth, the more slowly it's going to oscillate. So before we confirm that relationship in a video, the relationship between the mass and the frequency, let's first try to convince ourselves that the mass actually does move in this sinusoidal fashion. So here's one of those classic demonstrations from MIT. You don't have to go to MIT to see it. You can just pull it up on YouTube or enroll at your local city college in Long Beach. No matter what they do in these demos, they're always wearing a white lab coat. How cool is that? I scrolled down to the comments and there's a bunch of haters blasting this video. Some people just don't appreciate the science. But do you see what happens, or what's happening? The spray paint can is really attached to two springs, but together they act like one spring. And the oscillations are fairly small amplitude, so we can trust that these springs are behaving like Hooke's law springs. So this paint can should be in simple harmonic motion vertically. And by spraying the paint onto this roll of paper that's being forced to move horizontally, we've introduced that horizontal t-axis. And it sure looks like sinusoidal motion. It's a little distorted, right? That's not a pure frequency. You can see that this wavelength is just a tad longer than this one. And that's because he was regulating time manually by just unspooling that piece of string. If it was done with a motor more precisely, this would look more like a perfect sinusoid. This next little clip will demonstrate the relation between the mass attached to the spring and the frequency of oscillation. So the comments below this video, or the caption, explains that each of these three springs has the same stiffness. The only variable here is how much mass is attached to the spring. So light, medium, and heavy. So hopefully it's clear that this one bounces around most quickly. This one has the lowest frequency of oscillation. Remember, the mass is in the denominator under that square root sign. Now, cosine of omega t, where omega is the square root of k over m, that function is not the only solution to the differential equation. Another solution, for instance, would be sine of omega t. I mentioned that a moment ago. And even that's not the only solution. You can imagine that the actual function which describes how the mass bounces around is going to depend on the way in which you started the motion at t equals 0. So if you pulled the mass to the side and let it go at t equals 0, cosine of omega t would be the appropriate function. If you gave it a little push to the right at t equals 0, sine of omega t would be the appropriate function. Anything else, like anything in between, so to speak, would be covered by this general function here. So we still have the cosine of omega t, but we have what's called an amplitude out front, and it's pretty universal to use capital A for amplitude. And then this quantity inside the argument of cosine. Remember, everything inside the argument, everything inside the parentheses is called the argument. After you've done your multiplication here, omega times t, and added this quantity, whatever you're left with, the overall number inside the parentheses is called the argument, and we think of it as being an angle in degrees or radians. And this quantity is called the phase constant, sometimes called the phase shift. I believe this is the letter phi, phi, fo fum. And I'm using the same notation that your book uses. I'll try to be consistent in that regard. So once again, A for amplitude, omega for the so-called angular frequency. Technically, angular frequency and frequency are different. They differ by a factor of 2 pi. I'll talk more about that later. But the units of omega are radians per second, and then the phase constant, or phase shift. Now, the whole thing inside parentheses, I mentioned just a moment ago, it's called the argument. Sometimes it's also called the phase. More on that later. So let us avail ourselves of this awesome free online calculator at Desmos. We'll start with the cosine, and I'll just call it cosine of omega. I have to call it x, unfortunately. So we're crisscrossing the meaning of our variables, and that's because I haven't figured out how to rename the variables on this website. I don't even know if you can do that, but when I'm typing x right now, that really means t for time. So this horizontal axis is the t-axis. Now, cosine of t is the same as the cosine of 1 times t. So here's a function for which the angular frequency is 1. Omega equals 1. Let's first experiment with the amplitude. So what happens if I stick a 2 out front instead of just a 1? Cool. Obviously, it makes the peak of the cosine function higher. Instead of peaking at 1 and bottoming out at -1, it goes from 2 to -2. In fact, we can even add a parameter here. Let me put capital A, add a slider here. Ooh. And all I have to do now is drag the slider to the right or the left. So I'm increasing the amplitude, and I'm decreasing the amplitude. And again, right now we're talking about the oscillations of a mass on a spring. Later, we're going to talk about waves on a string. We'll talk about sound waves, even light waves, electromagnetic waves. I'll just point this out now. If we were talking about waves right now, if we were using this cosine function to represent mathematically a wave such as a sound wave, then increasing the amplitude would correspond to a louder sound wave. So the volume of the sound wave has to do with, or the volume that you experience has to do with the amplitude of the sound wave. If we were talking about light, you might guess that this has something to do with the brightness or the intensity of the light. Okay, can we add another parameter? How about omega? Now I can't type in the letter omega because that's a Greek letter, so I'll have to go with W, even though it's not a W. Let me add a slider for W. So remember, a stiffer spring, K is in the numerator under that radical, and we saw that a stiffer spring shakes around more quickly. So if I increase omega, I should see this thing oscillate more quickly in time. The horizontal axis is the t-axis. What happens if I increase omega? As expected, if this graph represents the motion of a mass on a spring, this mass is now bouncing around more quickly at a higher frequency. So a stiffer spring does this. And it's kind of just a coincidence that this sinusoid almost looks like a coiled spring, doesn't it? But that's not what we're looking at here. If I decrease the stiffness of the spring, then, again, this is not the spring we're looking at. This is a graph of the mass's position in time. As I decrease the stiffness, omega would decrease, and this thing's going to bounce around less quickly, or more precisely, with a lower frequency. Now, the last parameter we have to take into account is the phase constant. And again, that's a Greek letter, phi. So let me go with P instead, plus P. Add that slider. What's the effect of changing the phase constant? What do you think? Why am I asking you? You're not going to tell me. Oops, that's the amplitude. Let me go back up here. All right, so I'm increasing the phase constant, I'm decreasing the phase constant, and you can see that it just shifts the graph to the left or the right. Now, if I put the graph right here, where it starts at its maximum value, this is like cosine, right? Cosine starts at its maximum and then dives down, whereas the sine function starts at 0, like this, and goes up from there. So really the only difference between sine and cosine is what you could call a phase shift. It's actually a phase shift of 90 degrees. If P had a value of negative pi over 2, remember pi over 2 radians is the same as 90 degrees. Cosine of x minus pi over 2 is sine of x. And in this case, we're talking about sine of omega t. So they're both sinusoids, right? They both have the same curvature. The only difference is that phase shift. And if P is something arbitrary, like it's not negative pi over 2, then you get this graph which is neither cosine nor sine, but it's basically the same, right? And now I'd like to introduce some vocabulary that's actually not introduced in your book at this point, but especially those of you who are going to continue in physics and study quantum mechanics, you will see this later. You could call this special frequency the eigenfrequency of this simple mechanical system. If you just pull the mass to the side and let it go, there's only one frequency at which it will oscillate. That's the eigenfrequency. You could, of course, drive the mass at a different frequency. If you just, grabbed it with your hand and moved it around more quickly or more slowly, you could force it to oscillate at a different frequency, but left to its own devices, so to speak, there's only one frequency, and that's calculated very simply in terms of the stiffness of the spring and the mass. So the properties of the system determine that eigenfrequency. And I feel like the font wasn't fancy enough for that word. I think this word comes from German, and again, you're going to see this again. If you take linear algebra, you'll learn about eigenvectors and eigenvalues. There's a very close connection to what we're talking about here, although it's not obvious at the beginning. Now, why am I telling you this? Well, we're going to spend a lot more time this semester talking about waves on strings, for instance, than masses on springs. And a string can be thought of as a very large number of little masses, whether you want to think of those as actual molecules within the string, or just imagine chopping the string into a trillion pieces and calling each of those a particle. And they're all connected, and you can think of those connections like springs. And so we're really talking about coupled oscillators. So here's the simplest case of two coupled oscillators. Instead of a single mass on a single spring, you've got this left mass connected to, I'll call it the wall, by a spring. You've got this mass on the right connected to the opposite wall by a spring. And then there's a third, weaker spring connecting the two. And just watch the behavior of this mechanical system when set into motion with arbitrary initial conditions. If you watch closely, you'll see that neither of the masses is really moving at one particular frequency. Like, it looks to me like this one on the left almost seems to be slowing down. Its amplitude is certainly decreasing. And it's also interesting how the left one is practically stationary now, whereas it started out in motion. Let's go back. At the beginning, the one on the right's not moving very much, and the left one is. And then the roles are reversed. This is an interesting phenomenon that pops up often with these coupled oscillators. So this is a slightly more complicated mechanical system than just a mass on a spring, but I'm going to try and convince you with some other people's videos that we can still talk about these so-called eigenfrequencies. This guy, Dr. Dan Russell, has done a lot of great things for physics education. I think you're going to see more than once this semester some simulations that I put onto Canvas that were done by this guy.
Two pendulums of equal length are connected by a soft spring comprising a coupled 2-degree of freedom system. Such a 2-degree of freedom system has two natural modes of vibration.
He just said two natural modes of vibration. That's what I was referring to when I was being snooty and using the word eigenfrequencies. So this is slightly different from the little animation I just showed you. By the way, that animation was done by yours truly. I used Mathematica to make that animation a few years ago, and I've since totally forgotten how I did it. If you asked me to do it now, I couldn't do it. But in this video, instead of masses on springs, we've got two pendulums which are connected by a spring. So think of gravity as playing the role of those outer springs, the ones that were connected to the wall. Gravity is what pulls this mass back towards equilibrium. Same thing for this mass. Gravity would tend to pull it back towards equilibrium. And we do have a spring connecting them. Now, in the animation, the motion looked kind of, I don't want to say chaotic because that does mean something specific, but the masses were not oscillating at any one particular frequency. Here, on the other hand, you'll see that they do.
In the first mode shown here, the two masses move in the same direction at the same time, and the coupling spring is neither stretched nor compressed.
So if you pull them both to the right or to the left and release them, they will move together. They both oscillate at the same frequency. That's one of the eigenfrequencies of this system. And that motion is also called a normal mode or normal oscillation. I just noticed this guy's got a lot of baseball bats. Are these baseball bats? What's he doing with all those? You're getting very sleepy.
In the second natural mode of vibration, the two masses move in opposite directions, alternately compressing and stretching the coupling spring. The center of the spring is a node and does not move at all.
Now, it's not obvious, but if you pay careful attention, you'll see that they're now oscillating at a different frequency than they were previously. So let me back up.
Move in the center comprising a coupled 2-degree of freedom system. Such a 2-degree of freedom, two masses move in the same direction at the same time, and the coupling spring is neither.
Okay, is it just me, or is the next motion, does that comprise a higher frequency? Not a huge difference, but that looks a little quicker to me, and that can be proven. And it turns out that those are the only two normal modes of oscillation. If you try anything else, and I forgot to point out what you've done, or what he's done here, is pull them opposite directions before releasing them. If you start them off in any other arbitrary motion, like you push one to the left and don't do anything to the one on the right, then they're going to go into a less organized motion, kind of like the animation that I showed you. And that turns out to be what we call a superposition of those two normal modes. Now, it's no coincidence that there are two masses and two eigenfrequencies. If you had three masses that were coupled, you could find three eigenfrequencies. This is not really part of your curriculum in the book at the beginning of the semester, but I'm pointing it out because later we are going to talk about standing waves on strings. And you can imagine that a string consists of a really large number of masses. Because you know what a mole is, you know how small atoms are. Let's go with like a trillion different particles. That's an awful lot of possible normal modes. And I'm showing you this now so that you have that in the back of your mind, that a string arguably is a much more complicated system than a single mass on a spring or two masses connected by a spring, but you can still think of it the same way. They're still coupled oscillators that are capable of moving in a more organized way, like these two are moving now.
A coupled oscillation behavior occurs when both masses are released from rest, but one mass is at its equilibrium.
So what you're looking at now is neither normal mode. You're looking at a superposition. So you can't say that the system is moving in just one frequency or the other. Remember, there were two frequencies. It's a combination of both. Now, to make that comment more real, my observation about the connection between these normal modes and waves on a string, let's look at another video by the same guy.
A 1 degree of freedom mass spring system has one natural frequency and one vibrational mode shape. The mass oscillates back and forth.
So this is not a mass on a single spring, is it? It's really a mass connected by strings to an anchor point, and this is the driver here. This is what's forcing the oscillations to continue. But you can think of these two strings as behaving like a single spring. If you want, imagine a spring anchored on the ground here that goes up and attaches right there to this mass. It's very similar when you look at it mathematically. And as he just pointed out, there's only one frequency at which that thing can oscillate, one eigenfrequency.
Or in this case up and down, at a frequency that depends on the inertia or mass and elastic or stiffness properties of...
There you go, the stiffness, right? So the stiffness or elastic property of the string is analogous to the spring constant for an actual coiled spring. And I should have pointed out that having only one frequency of oscillation, I believe that's the simple harmonic motion. You may be familiar with the word harmonic as synonymous with sine and cosine. Sine and cosine are sometimes called circular functions or harmonic functions. So I believe the simple harmonic motion means motion at one frequency
of the system.
I'm going to skip around a bit here.
Spring system has two natural frequencies and two mode shapes. In the first mode shape, first frequency, the two masses move in the same direction at the same time, basically looking like a 1 degree of freedom oscillator.
Hey, can you pass the popcorn, please? This is riveting.
In the second mode of vibration,
now it's really obvious, is it not, that this eigenfrequency is significantly higher than the last one. Two masses, or 2 degrees of freedom, as he calls it, two eigenfrequencies, not a coincidence.
the two masses oscillate in opposite directions, one going up while the other one's going down. At the very center in between the two masses is a node, a point that doesn't move at all. Then three mode shapes. In the first mode shape, all three masses move in the same direction at the same time.
Okay, sorry to cut you off, Dr. Russell there. There's the first eigenfrequency. I think that's the slowest. Let's fast forward to the next one.
At a node point, while the two outside masses move with
definitely faster, right? And an important property of the motion here is you'll notice all three of these masses are oscillating at that same frequency. It's not like one of them is bobbing around at a higher frequency than the other two. They all move at the same frequency. That's a characteristic of a normal mode of vibration.
opposite phase in opposite directions.
Okay, what's the third one?
3 degree freedom system. All three masses alternate in
Hopefully it's clear that all three of those different motions had different frequencies. I think the last example is 4.
directions. Two in the center, but the entire system moves in the same direction at the same time.
One eigenfrequency.
Right half and the left half move in opposite directions.
There's the second one.
The inner pair.
It's getting harder to guess these, right? Like with two masses, you probably could have guessed what the two normal modes look like. With 4, maybe not so much. And with 10 to the 23rd, is that even possible to guess what those normal modes would look like? Well, we are going to look at those later. Those are called standing waves on a string. Let's briefly revisit the two coupled oscillators and bring Newton's dynamical result into the picture here. So I'm going to apply F equals ma, Newton's second law, to the mass on the left here. And I'm using capital K for the stiffness of these outer springs. They have the same stiffness, and lowercase k for the stiffness of the coupling spring. And remember, little k is supposed to be a smaller number than big K. So I'll rewrite the acceleration as the second time derivative of position 1. And we know we're already looking at a differential equation, because not only do we have, oh, you know what? I should have labeled this x1 right here. This should say x1. Where's my laser pointer? Okay, so I've plopped in two forces now. I've applied Hooke's law twice. Once for the spring that connects the mass to the wall. That's just straight up Hooke's law. But then I've also got the interaction between the two. So x2 minus x1, I'm not going to go into the details of the coordinate system here, because this is really just for illustrative purposes. We're not going to solve this particular problem. But this is basically how much the in-between spring has been, the coupling spring, has been stretched or compressed. And there's no minus sign here, because if this spring is stretched, it would actually pull mass 1 to the right. That would be a positive force, hence the plus sign. But I believe this is the correct dynamical law for the motion of x1. And you'll notice that x2 makes an appearance in this equation. Again, I should have labeled this right here x1. So not only do we have an unknown function x1, that's a function of time, we also have its second derivative in the equation, and we have a second unknown function of time, x2. That's the position of mass 2. We could go over to the right mass now and write F equals ma for that mass, and we would have a second differential equation involving the acceleration of mass 2, which I could call x2 double dot. And we would call that system of equations a two-coupled second-order differential equation. Second order because we see the second time derivative. So the equations are referred to as coupled, and it's no coincidence that we say the masses are coupled. So the force experienced by this mass on the left depends on the position of the second mass. If the second mass is really far to the right, this spring will be stretched more and exert subsequently a greater force on mass 1. So the positions of the two masses affect each other. That's the coupling. This is the coupling term right there. Now, I'm belaboring this point because while it's not covered in your book, something really more challenging is covered very soon in the next chapter when we talk about waves on strings, where we see that each particle of the string is coupled to the neighboring particles. And we're going to see another differential equation that's actually a partial differential equation. That will be discussed in the next chapter. The last thing we need to talk about as it pertains to the simple harmonic oscillator. So SHM is simple harmonic motion and SHO is simple harmonic oscillation. That last topic is the energy, because this is referred to often in the subsequent chapters. So let's look at the energy of a simple harmonic oscillator. We know that the total mechanical energy has two forms. It's a combination of kinetic energy and potential energy. Those of you who go further in physics, in future books, you'll see capital T used for kinetic energy. I couldn't tell you why, it's probably historic, but we like to use capital T in this class for the period of oscillation, which I haven't discussed yet in this video. So we'll go with capital K for kinetic energy, not spring constant. This capital K is kinetic energy, capital U for the elastic or spring potential energy. And let's see if we can evaluate this, because we've now determined for a particular choice of phase constant, I've put phi equal to 0 here. We know that this is how the position depends on time. A is the amplitude, omega is the frequency. We take the first time derivative to get the speed. That's such a hard word to spit out. Derivative. First time, how many syllables is that? Derivative. Every time we want to say derivative, we have to use 4 syllables even though it's one of the most common ideas we express in physics. It's a shame we don't have a shorter way to say that. Okay, well, we know that kinetic energy is 1/2 mv squared, where v is the time derivative of position. So we'll take this expression for x dot, plug it in there, and we know that the potential energy is 1/2 k x squared. It's that parabolic or quadratic dependence on position. Again, this is only applicable to an ideal spring. A Hooke's law spring has this form of potential energy. So let me make those substitutions. I get this, and this is looking kind of gnarly, but this simplifies nicely because, remember, the angular frequency is calculated this way, the square root of k over m. So why don't we square this equation and solve for k to get this? I have this memorized because I've seen it so many times. You don't have to memorize it, but k can be re-expressed as m omega squared. Let's take this and plug it in to k there. See how I highlighted it in blue to draw your attention to it? A little courtesy highlight there. When you look at this, do you get the itch to do anything in particular? Do your impulses from high school trigonometry or pre-calculus come back? Notice how both of these terms have a 1/2 m omega squared a squared in front of them. So you could factor all that out, and what could you do with the sine squared plus cosine squared? Well, regardless of what the number inside the parentheses is, sine squared plus cosine squared is always 1. And believe it or not, that's even true if you plug an imaginary number into the parentheses. So the sine squared of I plus the cosine squared of I is also equal to 1. And we're left with this. Simple expression. Well, I can... Well, my computer just slowed down on me, so I'm sure the audio cut out there. Sorry about that. Very simple expression for the total energy, and let's make that substitution one more time. M omega squared can be replaced with K, and there's the total mechanical energy of a simple harmonic oscillator if we're talking about a mass on a spring. The other archetypal simple harmonic oscillator is a pendulum, a small amplitude oscillation pendulum, but right now we're just talking about a mass on a spring. And you could have gotten to this result more quickly by remembering how to interpret an energy diagram. So this dashed red line represents the 1/2 kx squared potential. So this is really the x-axis. That's why they've called it displacement. As you move the mass to the right or the left, the potential energy that it has rises quadratically. Now the height of this purple line here represents the total mechanical energy. And we know that if you take the total mechanical energy and subtract the value of the potential energy, what you have left is the kinetic energy. So the blue line shows you how the kinetic energy depends on position. As your mass moves outwards, it gains potential energy. That's the upward sloping parabola. And it loses kinetic energy. Now, when it gets all the way out to this point right here, that is where the kinetic energy has gone to 0. In other words, the particle or the mass has stopped and it's going to turn around. That's the amplitude of the motion. So you could just recognize that when the mass is at its turning point, it has all of its energy associated with potential energy. Any kinetic energy it had was transformed into potential energy. So you can just use 1/2 kx squared and evaluate x at the amplitude. That's another way to get the expression for energy. So you will see this in subsequent chapters when we're talking about energy flowing down a string as a wave carries energy through the string. And the book will make reference to how each of the particles in the string are executing simple harmonic motion. And we know that the energy of a simple harmonic oscillator is proportional to the square of its amplitude. That's really the takeaway there, that the energy of an SHO is proportional to the square of the amplitude. And the constant of proportionality has to do with the elasticity of the system. And that concludes our very brief but hopefully sufficient review of simple harmonic motion.